Okay, wonderful. So I would like to share some ideas about the project. The project for undergraduate student with experience of introductory differential equation. The project is based on actual observations. Oh, what happened? I cannot move my slides. Okay. So the project is based on real observations of oceanographers, real data parameters, and the results, the ideas were published in oceanographic journals. As we know, the world ocean is polluted with microplastics, and oceanographers observed that the particles submerged in the water are getting broken into very small components. These smaller components of microplastics are can be 10 to the negative 6 meters radius. They're very tiny. And when they break in these small components, oceanographers find that they would expect to see significantly higher number of these components. So microplastic is getting lost somewhere in the ocean, and it is important to understand where to search for these islands of microplastics, where to search for microplastics. Of course, this is a toy model, so it's not exact recipe where to find microplastics in the ocean, because there are lots of weather conditions. There are we are not taking into account the waves and all changes of the ocean. We assume that the water is still water, but we will discover some dynamics in this still water, dynamics of microplastics that bonds with algae. Usually, density of microplastics is lower than the density of water. So microplastics are supposed to float on the surface of the water. When it bonds with algae, it tends to sink because algal cells are denser than water, or about the same density as the density of water. The density of water in the ocean is not constant. It's increasing with the depths, and it's increasing by approximately 3 kilograms per cubical meter until the so-called pycnocline depths. A pycnocline is located at different depths in different locations, but we will assume that it is approximately at 1,000 meters. And so the density of water in the ocean is increasing until 1,000 meters, and then it stays constant. So what happens? The microplastics submerged in the water gets broken into these smaller components. It bonds with the algal cells, and this biofilm gets heavier while algal population is growing, number of algal cells is growing, and this heavier aggregate sinks towards the bottom of the water, of the ocean. Then it gets into the place where there is very small or no light exposure, and the conditions for algal growth are bad. So then algal cells die, they disappear, plastic gets lighter, and it goes back towards the surface of the water. But when it gets towards the surface of the water, the conditions get better, so then algal population grows again, and this cycle may repeat. So the observations of oceanographers were assumption, so some hypotheses were that this these aggregates of plastic with algal cells is cycling up and down. So it was actually a published result, but let's see what our model shows. So I will construct a three-dimensional system, dynamical system, and there are going to be one equation that is a population dynamics equation. It shows the rate of growth of the number of algal cells, N. Two other equations are the Newtonian dynamics equations, and they are based on the second law of Newton and hydrodynamics friction. I will use here Stokes formula. So the axis is going to be pointing towards the gravitational, the same direction as gravitational force. The depth of the ocean is going to be Z variable. And since we are mathematicians, so let's write down some formulas. So dNdt will be, as always, growth rate minus death rate plus attachment of new cells. And the motion equations, it's equation of velocity, and the second law of Newton, so mass, the mass of this aggregate times acceleration is the mass times gravitational constant minus the mass of the water, mass of the displaced water times gravitational force minus some friction. The interesting thing is that now growth rate depends on the depth. We will assume that death rate is constant, and the attachment rate also depends on the depth, because in the deeper waters, there is a smaller chance of new cells to attach to this aggregate. The motion equations also involve n parameters. So the mass of this aggregate depends on the number of algal cells. The mass of the displaced water depends on the n, and friction depends on the number of cells. To be even more precise, now I will write all the formulas. So the constants that we can perturb, something that there is a wide range of constants, so we can work with them. I write them in red. So rate of death is constant, as I said. The volume of the plastic particle is another constant. Volume of algal cell is a constant. Corresponding densities of microplastic and algal cell density. And there is some constant associated with the friction. I use here, so it's proportional to kinematic viscosity. There are some other constants, but I hide them under C constant. There are lots of constants here. So for friction, I use Stokes' law, but there are other ways also to describe friction. Stokes' law assumes that this aggregate is a sphere, but one can use some drag force where velocity will be quadratic, and it will depend also on the surface area. Here I have dependency on the radius of this sphere. Then also the radius is proportional to the cube root of the total volume. Total volume is here, so we can further simplify this expression. So this is the final system that that we can study. Now, the functions growth rate of algal cells. So growth rate decreasing with depth, and this is the green graph. The rate of attachment depends on the light intensity, and light intensity is the highest somewhere around 25 meters depth, according to some publications. So these are the functions that are also going to participate in our study. Okay, so what can we do with these equations, what students can learn from this system? So the first thing is probably to study the simulations. And if we run the simulations for this system, I put here depth versus number of algal cells, and depth here is on the log scale. So we can see that first, the number of particles, algal cells is growing, very rapidly growing, and the depth is increasing. And this happens until certain depths where the growth is no longer possible, growth of algal cells. So then the depth and the number of algal cells decreasing. And you can see that here depth, the aggregate is going towards the bottom, towards the surface of the water. At this point, I have magnified fragment of the graph. So at this point, the particle oscillates up and down, and the number of cells is also going up and down until it comes to the equilibrium. So it's approaching equilibrium state. So another part that students can learn in this system of equations is to study stationary points and to see the properties of the stationary points. For the purpose of this presentation, I decided to consider actually a bit simpler system. I decided to cross out this attachment rate. So I will consider the system without new cells being attached, but the properties are going to be very similar actually to the original system. So students can see stationary points, and it's easy to understand physical meaning of these stationary points. The most obvious condition is probably that velocity must be 0. So this is first variable that is obviously 0. Then, in order to find equilibrium in the first equation, we can see that the rate of growth of the new cells must be equal to the rate of death. And this defines the depth where equilibrium is found. So the equilibrium will be located at the depth where appearance of new cells is the same as the rate of their disappearance. So at this depth, we can find how many algal cells are required to bring this aggregate to this depth. And this is going to be equilibrium that we calculate with the third equation. There is actually another point. So this is equation for the first equilibrium point with V equals 0. There is another equilibrium here when n equals 0. But if we set n equals 0, then we will see that the density of water must be the same as the density of a plastic particle. And this is not really possible because plastic is usually lighter than water. So I will not actually consider this equilibrium. Okay, so we found the equation for equilibrium. And now we can try to see what happens if we change parameters, if we perturb parameters. For the parameters of such systems, there is a very wide range of possible values. They depend on the geographic location, so they depend on many different factors. And it is important to consider stability with respect to perturbed parameters. So let's try to perturb, for instance, the density of algal cells. So we have this hyperbola that describes stationary points, number of algal cells required for this aggregate to come to the fixed point. at the depths where rate of growth is the same as the rate of rate of death of algae. Okay, so let's study stability. We can consider linearization. So we have this matrix of first derivatives. And with our conditions that the density of algal cells is higher than the density of plastic. Also, the rate of growth of algal cells is a decreasing function, and the density of water is increasing function. From these conditions, we can see that the characteristic equation has all positive coefficients. And then Descartes' rule implies that all roots have negative real parts. So we have the stability, all equilibria on this curve, all points of equilibria are stable equilibria. So it shows that in a wide range of possible parameters, stability persists. And of course, another question is, what if we add attachment functions? So how can we analyze this system, possibly involving some numerical calculations? So there are some questions that can be studied related to specific locations. So probably there are some interesting questions that students can discover with this system. And this is probably the end of my presentation.
Thank you.
I will stop sharing. And thank you so much for your attention. Christoph?
Can I ask one question? This was very, very interesting. I really liked it. One question I had was, you assume that the death rate doesn't depend on depth, and I naively would have thought when these algae go too low, they die out. So would that make any difference if you made the death rate depend on depth, or should it depend on depth really, or not?
Well, in the publications that I considered, it was constant, but I agree that it would be reasonable to consider non-constant rate of death. So we would have a difference of birth minus death times number of algal cells. So this would be a new value for the coefficient. And so the it would depend on the sign of the new function. If it's increasing, decreasing, so then it would define the behavior. And it would be more interesting study.
Might it make a difference for the question whether there are ever
stability?
Yeah.
We'll have to see the sign of the derivative of the difference of these two functions.
Yeah, I would have thought that algae probably need some light, right? If they go so low that they don't have enough light, I would think that they die at higher rates. So.
Definitely. It would be another interesting question to add here. I think here, this assumption is kind of absorbed into the lower rate of growth, but it's better probably to make rate of death non-constant, to create another function and then to consider the difference of those two. And their derivative is involved in the stability.
Thank you.
Yeah, that's another interesting question to ask students to add to this thank you so much for it in this direction.
So the papers that say that there are these oscillations, right? That seems like a really interesting phenomenon. Do they have experimental evidence for that, or why do they think that they exist?
Well, there was sort of conjecture that probably plastic should go up and down. There was one paper where there was kind of a proof, but I'm not sure about mathematical details there. So I'm not sure if there are empirical confirmations of this behavior, or it was just sort of assumption. When one thinks about dying and growing again, it's natural to assume this periodic behavior. But I'm not sure if it was really observed. I didn't see this kind of clear statement. I think it was just like possibly they go up and down.
Yeah.
So from mathematical point of view, with this model, I'm not sure if it's going to show periodic behavior.
Uh-huh.
Even if they change rate of death to non-constant, well, one needs to see.
You had the attachment rate also neglected, right? The A of Z in your equation, and that make a difference potentially?
No, actually, with the kind of reasonable range of parameters for attachment, they were all tending towards stable equilibria. For those parameters that are within some reasonable range.
Hmm.
Yeah, but lots of great questions that can probably be added to this model.
Well, I think you've been dealing with an extremely complicated system, and you've given us some handles to start looking at it, and that's very helpful.
There are also simulations that students can probably run, and so some questions can be studied numerically, probably, to get some initial ideas about the behavior of the system.
Mm-hmm.
So knowing the answers to these questions, like, for example, whether it's at a stable height or whether it oscillates in height, would that have consequences for what people do? Let's say, I assume, I have no idea, but I would assume that people try to remove microplastics from the ocean. Does it have consequences for efforts to remove it or something like that?
Well, of course, the behavior of the ocean is very complicated. I assume that the water is still, but of course there are waves and streams and lots of other conditions of the ocean. But if one uses the idea of this model where for instance, the depths must be the level where rate of death compensates rate of birth, appearance compensates disappearance. So one may try to search approximately at this depth to search for location of the plastic and possibly to remove here. If it oscillates, then probably within the range of oscillations, maybe the removal can be initiated. But I don't know how big is the effect of the actual streams and waves of live ocean water.
Hmm.
in actual number of feet, how deep is that equilibrium depth that you find?
So it is, everything is measured here in meters.
Meters,
So it's 60 something. So the equilibrium that I calculated, it was with the parameters. I actually used not Stokes formula for the drag force, but I used drag force which has quadratic component of the velocity, and instead of the radius, it has surface area and slightly different coefficients. Then it allows also different shapes, because here we assume that particle is spherical. If we use drag coefficient with quadratic velocity, it allows also to use different coefficients for different shapes. And with this drag force, I found 62 meters or something around this depth, the equilibrium, 62 meters approximately.
Thank you, Christoph, for all those good questions.
A really fascinating
Yeah.
talk. Really interesting story.
Thank you so much for great questions, everybody. Thank you.
I have to leave, but thank you very much. Both
Thank
of you.
you. Thank you for the opportunity to present and for the great questions.
Thank you. Bye.